My name is Saborno Isaac Berry from Berry Science Lab, and today we'll be taking a look at applying Lagrangian mechanics in physical situations. So, as we derived the other day, the Lagrange equation looks like this. So, you have some function y, which itself is a function of x, and so this equation holds true if you want to optimize L. So now we're going to figure out a specific L that we plug in order to turn this into Newtonian mechanics that we already know. So, of course, when we're dealing with physical situations, our function will probably be position of some sort, and the variable of that function will probably be time, even though it can vary. Sometimes this can be position and this can be position. Sometimes this can be velocity and this can be time. Sometimes this could be angle and this could be time. Sometimes this could be angle and this could be position. It really depends on what scenario you're looking at. So then you have d dt, partial L, partial x prime of t, which you can sometimes write as x dot. So this is the equation that we have. Now, how do we turn that into the Newtonian mechanics that we all know and love? Well, here's one thing you should notice first of all. When you take this derivative, L, well, what is L composed of? We can do a little bit of dimensional analysis, but let's just get into it ourselves. Partial L, partial x dot. L is a function of x dot, and t always, nothing else. So then that means when we take this derivative, it will still be a function of x dot, and t. But when we take this derivative, it will be a function of x dot, and x double dot, which is analogous to acceleration, and of course t. And so that means that on this side we will get an x double dot term, which is acceleration, which means that we have to put in all our effort to making sure whatever is on this side is m x double dot. In other words, we have to make sure d dt, partial L, partial x dot, is m x double dot. And that can be made pretty easy by just integrating with respect to time on both sides. And then integrating with respect to x dot on both sides, which gives you half mx double dot squared plus some function of x and t, and this right here is partial, just L. So, would you look at that, we have kinetic energy right there, just sprouting out of the dark. So what's this constant function? Oh, well, it's not a constant function. But what's this function right here that gets treated as a constant when we differentiate with respect to x dot? Well, let's find out. When we differentiate with respect to x, this obviously will disappear, meaning we're left with that tiny little function. So we'll say partial h of x and t, partial x. And that's, of course, equal to mx double dot, which means this has to be equal to force. So, what is force? You can probably remember that potential is the negative gradient of force. And if you don't know what a gradient is, it's a fancy word for a vector that acts kind of like a derivative in multiple dimensions. So it has the partial derivative in the x, the partial derivative in the y, and the partial derivative in the z. So it's a positional derivative, essentially. If we reduce it to one coordinate, the gradient is technically a scalar. So we just have partial f, well, negative partial f, partial x, which means that whatever this is, it should be equal to negative partial f. Well, no. It should be equal to negative partial u, partial wave. Let me just make sure. Oh, crap. Force is the negative gradient of potential. I'm so sorry. So, this has to be f, so this has to be equal to negative partial u partial x, which means, of course, this function right here has to be equal to negative u. Which means that our Lagrangian is just half mx dot squared, which is k minus u. So, that's our final answer to making sure that this is equal to Newtonian mechanics. Now, can we see an example with that is the question. So, let's look at this pendulum and solve it two ways, Newtonian and Lagrangian. Okay, so first let's solve it the basic Newtonian way. How do we do that?
What are you solving for, velocity?
We're solving for the position function over time. So this object currently has two forces acting on it. The force of gravity and the force of tension from our magic rope that somehow always stays sturdy in a straight line and doesn't change length and has no mass. You know, this rope is really useful for all kinds of stuff. So, let's say this rope constantly has length L, and of course, because of the way ropes work, they will always be providing only enough tension to resist the force that's pulling it the other direction. I mean, otherwise, it would accelerate randomly while it was on a rope for no reason. Like, as you can see, this guy over here, he's not suddenly accelerating upwards because the force of tension and the force of gravity, the force of tension only exerts enough force upward to counteract the force of gravity. Doesn't need to do any more.
Yeah, it's pendulum.
Yeah, but it's not swinging in a straight line, as you can see. Now,
Why it doesn't swing like a pendulum? Is it because the mass is not heavy enough?
no, it's generally because a rope, it can curl.
Oh,
And in this case, it actually didn't curl all that much.
sorry.
In this case, if you look closely, you can see that it had a knot tied about midway through, so when you started swinging it, it actually acted like a double pendulum, which we'll be covering later, in which you can see again, if I just, as you can see, it's acting like a double pendulum, right? It's more effective if I swing it harder. Oh, wait, it's not acting like a double pendulum either anymore. As you can see, the angle of the first half of the rope and the second half are slightly different until it settles down. So, back to the topic. Now, we need to figure out, well, first of all, what's this force? Second of all, what's the only force making it move? So the only force that can make it move is the force in this perpendicular direction. So let's pretend that currently this object is angled at theta. Now we're actually going to use polar coordinates to quantify this object's trajectory. And then later, we can convert it over to Cartesian. So, let's see. This fella right over here is what? This is actually way too big to be to scale. So, it would be something more like this. So, as you can see, we have the makings of a right triangle. So, it's not perfect, but. So, of course, we already know that this angle right here, by interior angles, is the same as this theta. Now this, the length of this vector is FG, which means this vector is FG sine theta, and this vector is FG cosine theta. Now, we only care about the perpendicular direction because this parallel one is being counteracted by the force of tension. So we work this out of existence, and the only force we care about is Fg sine theta. Now, by how much is it affecting our little pendulum right here? Well, we'll have to figure it out this way. So, the force acting on it is Fg sine theta, right? And what is force equal to? Mass times tangential acceleration. But what is tangential acceleration if not angular acceleration multiplied by r? Matter of fact, I sometimes forget whether it's multiplied or divided by r, but you can think of it this way. If you have a little CD and you're putting it into the CD player and you place a small object over here and a large object and a small object over here, much farther away from the center, then this object and this object are obviously going to spin with the same angular velocity, but bigger radius, bigger linear velocity. Has to cover much more distance in the same amount of time. So that means bigger radius, bigger velocity, you multiply by r. Anyway, forget being sidetracked. So we know mg sine theta is now equal to m theta dot dot. And we can cancel this out, but ultimately this is transcendental, unless of course we take, for small theta, then we get, and what does that give us? Well, this is characteristic of a trigonometric function, such as, I don't know, let's call it e to the, what should we call? Let's try sine of the square root of gt, right? What does that give us? Well, that will give us root g cosine of root gt, then g of negative g sine root gt. So we have to add a negative sign in here. But don't worry, that doesn't mean anything is imaginary because g is negative. So this is the solution to our equation. It just swings with the frequency dependent on the gravitational force, which means it actually doesn't depend at all on the length of the string or the mass of the bob. It only depends on the gravitational constant. Now let's solve it the Lagrangian way.
Oh, so you did it Newtonian way.
Yeah.
Okay.
So I'm just going to keep this up here as a reminder.
This is the final answer?
Yeah.
Theta is equal to sine the square root of g. You cannot have negative inside the square root, right?
G is negative.
Oh, negative 10. Oh.
Yeah. Well, it's not 10, but... And of course it varies based on what planet you're on.
Oh, that's true.
Well, I don't know. I just erased it.
It's okay, baby.
Okay. Well, we can always redraw it.
Yes.
So, now, what are we dealing with? What are we dealing with?
We are trying to find the position function using Lagrangian.
Now, the Lagrangian is kinetic minus potential. Now, we don't have any special kinds of potential energy here, so kinetic energy is just half mv squared, and potential is just mgh. Now, I'm going to convert that to polar coordinates. This is just theta dot, which you can also call omega if you want, divided by t squared, why did I say t? This would be r squared, minus mg. We'll deal with this fellow later. Or we can deal with him now. Yeah, we can deal with him now. Because in polar coordinates, you can always define y as just being equal to r sine theta. But the kind of theta we're dealing with is a little bit different here. We're instead dealing with something like this, which means that our y is going to be a little bit different. So we'll just keep it as h for now. But not for long, because we can define h. Let's set h equals 0 to be the exact midpoint of this guy's swing. So then, if it's right at the midpoint, that means that this is theta right over here, and we can also call it its lowest point. And so we have that this has length L, this has length L, and this right here is theta, which means this is L cosine theta. And so this is L minus L cosine theta. So the height above the ground is L, or R, because the radius is constantly the length of the string, minus R cosine theta. For context, imagine that our origin is way up here at the base of the pendulum. So now we've got everything converted to polar coordinates. We can just solve it. So we have partial L, partial theta is equal to d dt partial L, partial theta dot. We plug in. Now, of course, if we do partial L, partial theta, this guy gets wiped because it's a function of theta dot and r, and this function stays. So let's plug that in. We get partial theta of minus mg times r minus r cosine theta. By linearity, I'm going to take the constants of minus mg and r out of the equation, only leaving this, which is very easily differentiable, as sine theta, because the 1 goes to 0 and the negative cosine theta gets differentiated as sine theta. And of course, what is that equal to on the other side? d dt. And does this remind you of anything? For context, what we got on the Newtonian mechanics side was this. So, does this ring any bells? And does it look similar in any way?
Yeah.
Okay. So we have d dt multiplied by partial L, partial theta dot. And so, what's that going to give us? This guy gets wiped. We only take the derivative of this one, which is going to be, once again, by linearity. We leave out the half mr squared, because that's a constant. Partial theta dot of theta dot squared, which is just 2 theta dot. And of course, this guy gets converted to, take this out by linearity again, and take this out as well, canceling out the half, because half times 2 is 1, of course. And then, of course, taking the derivative with respect to time of theta dot is theta dot dot. So we get minus mgr Ah, crap, I missed something here, didn't I? Is equal to ddt of mr squared theta dot dot. So you get minus g is equal to ddt. Wait, why did I include the ddt? That's a 0 IQ move. And how did I forget to include the sine theta? So you get minus g sine theta is equal to r theta dot dot. And it looks like I've actually made a mistake because the frequency is dependent on r. We literally got an answer less prone to mistakes.
Oh, so Newtonian mechanics gave you the wrong result?
Well, I made a mistake when doing Newtonian mechanics because of how cumbersome it is.
Oh.
But Lagrangian mechanics is simple and easy, and so we are able to get the right answer every time.
Oh, so you want to fix Newtonian mechanics now?
No.
Okay.